Let me quickly introduce and also the event. So this is one of a kind where we are organizing a virtual paper presentation. So the idea is to call out multiple researchers who are working around various kind of problems around AI, and provide a forum where a fellow academicians or practitioners or researchers can connect with these papers. So this is our first event, and we believe we will continue this maybe one in every quarter or so. So as of now, we have close to 16 presentations across different problem statements. We finished almost 6, 7. We have another 3 for the day. So we have almost 6 tomorrow as well. And a quick background about SSI Club. So this is an open source club where we are bringing in multiple stakeholders from academia, researchers, enterprises, VCs, and startups. One, to share ideas and to fund open source ideas, particularly around safe superintelligence as we go towards AGI and SSI. So that's the intent. Having said this, let's get started. Once again, thanks Oussama for joining. So we are very excited to have you. Feel free to now take over the session. So please introduce yourself, and we are very excited to understand why you started on this problem statement, and your observations on the paper as well.
Yeah, thank you for inviting me. So yeah, maybe I will quickly introduce myself. So yeah, I'm just I think I have a classical background. So I'm just like I just obtained my master degree last year, but I have pretty much a theoretical background. So I mostly studied mathematics. Last year, so pretty recently, I was doing an internship at Huawei in a research lab in Paris. And yeah, basically we decided to tackle the problems of try to understand what happens in a probabilistic point of view and inside large language models. So yeah, it's just started like this, and yeah, at the end we produced this paper. So I will just maybe share my screen to maybe start now the presentation. All right, so just if you can confirm that you can see the screen and that everything is good.
Yeah, Oussama, we can see the screen.
Okay, perfect. So I have done this paper with my colleagues, so Ambroise, Abdelhakim, Linus, Nicolas, and Yevgen when I was at Huawei. So they are from roughly Huawei in RIA and Imperial College London, where I am actually based. Perhaps let's just get started and dive into the presentation. So I will just quickly introduce a bit some background knowledge, and then I will step by step present some contribution of the paper, and after we will discuss the presentation. Yeah, so one first thing I want to talk about is basically how we do probabilistic modeling on language. And basically, the best approach so far is to do autoregressive modeling, language modeling, which has the next goal. So you just want to predict the next word based on the previous ones in a sentence. So for example, you have this sentence, you have those previous words, I am the, and yeah, you just want to predict the next word. So in this case, it will be danger. So this is how we can model this is how we do autoregressive language modeling. And in a mathematical way, basically, if you have a sequence of n, let's say words, or we can say tokens in a more specific vocabulary. Basically, the goal is to like compute the probability of the joint event of basically each word in the sequence. So this is a really difficult problem because if you have n words and if those words can take, I don't know, let's say d different value, this will be exponential. It will have an exponential complexity in terms of the number of value d that your word can take. But by just using a chain rule like this, so writing this joint probability as just the product of conditional probabilities, basically you can just like see this problem as a linear problem because you just have like a multiplication of n single probabilities. Yeah, so basically you now have a complexity of like n times d, and this is really important because this way of modeling the language is scalable. And the other reason is that this is a really natural way to modelize language because like you just consider like you introduce a kind of natural order. So basically you consider the previous words in a sentence. And yeah, this is kind of really natural, and that's why it works so well. So yeah, to handle this probabilistic modeling, we have built a lot of models, and the best model so far is what we call the transformer, right? So basically, if you have a transformer, if you have enough compute, enough parameter, enough data, you can use this architecture, mainly the right part of this architecture, to basically build your own language model. And this is how current large language models are built. So for example, ChatGPT and his cousins. But yeah, basically those like we want to do math on those models. This is really challenging things to do. So to do so, we will just define those models with those parameters. So basically, I will just introduce the three important parameters. First, there is the vocabulary size. So basically, when you deal with language modeling, you fix a vocabulary space or a number of words that you will have and that you will deal with. You will have also a fixed number, which we call context window. So denoted as k. I will explain in the next slide what is this number. And yeah, basically you have, so a transformer is a neural network, so it has some trainable parameter. And yeah, so just to put some numbers, yeah, for GPT-3, for example, the vocabulary size is roughly 50,000. The number parameter is 175 billions, which is quite huge. And yeah, and the context window is this pretty small number of 2000. And yeah, what is a context window? So you know, this kind of language model, they process sequences in a particular way. So for example, if you have an input sequence of, let's say, 4 words, so for example, yeah, those 4 words, and that your language model has a context window of 7, basically, when you will input the sequence, the model will process the whole sequence like this. But if you have a sequence of more words than like just the context window, it will just it will just kind of forget the first word of the sequence and just process the last ones. And maybe you already have experienced this. Maybe like, I don't know, 1 year ago when there was GPT-3 only on ChatGPT, you know, you have this pretty small context window of 2000. And when you are chatting with ChatGPT, maybe sometimes it was like, yeah, the LLM just, it just forgot what you have said like 10 minutes earlier. So this is because of this mechanism of context window. Yeah, because it's like it deletes previous words or tokens. So yeah, this is really important to explain, because this will be at the core of what will be going. So now I will just talk about the second part of the title of the paper, which are Markov chains. So yeah, I will just do a quick recap on what Markov chains are, especially finite state space Markov chains. So basically, you have a set omega of, let's say, value. So you have some value, and a Markov chain is a sequence of the sequence of states. We call this value states. The sequence of states where basically the probabilistic modeling of the current state depends only on the previous one. So mathematically, it just means that, yeah, for example, if you want to predict the next word in a sequence, it will just depend on the last word, on the last element of this state space, and it will just forget the other stuff. So yeah, this is basically what we call the Markov chain. And one question that we can try to answer is, but are LLMs really Markov chain? Because yeah, if we take our example, so with the sequence I am the danger, if we want to predict the word danger, clearly, as we explained, it is not like the whole previous sentence is important, not just the last word, not just the last word. So clearly at the token level, an LLM LLMs do not implement Markov chains at the token level. But you know, there is this idea that, yeah, there is this just previous sequence. So by considering the previous sequence instead of the previous word only, maybe we can do something. So this means that as the state space of our Markov chain, we will not consider just the tokens. So the size of our set will not just be the number of tokens we have in our vocabulary space. It will be something else. So yeah, basically the idea to explain why LLMs can be seen as Markov chain is to consider the whole sequences. And this is why the context window is important. You will see just after, because the fact that this context window is a finite number will allow us to do so. So let's dive into the next part. Yeah, so let's say you consider your vocabulary space of size t, as we already said. What you can do is, as a state space for your Markov chain, you can consider just a set of all sequences consisting of elements of this space. So you will just construct all sequences that you can imagine, but just up to k elements. And maybe you will ask me why. This is because of the context window mechanism. Because if you input a sequence of more than k elements, basically the model will not see the previous element. So it's useless to consider sequences of length greater than equal k. So yeah, you will just define your state space as this, and thanks to this, you will be able to formalize a large language model as a Markov chain. So you know that you can formalize a Markov chain with its transition matrix, so which is basically a matrix with the states annotated on each rows and on each columns, and it will explain with like it will give you the probability to transition from one state to another. So it is, yeah, this matrix representation. And for example, if we look at this little part, for example, here you have all the sequences of length 3. And yeah, when you are generating just the next word, you will just add one word. So basically, there is a mapping between the sequences of 3 words and sequences of 4 words. And this pattern will give you a very structured Markov transition matrix. So like this. And we call this kind of matrices unit chains. So this kind of Markov chain, we call this unit chain. So it has a full theory to back up, you know. But yeah, maybe one thing that you will say is that, but what is the size of the state space? It is huge, right? And you're right, because the size of the state space is these numbers are roughly t to the power k. So it's exponential in the context length of the LLM. And yeah, so for GPT-3, for example, this is basically this huge number, which is really huge. For example, I can tell you that we estimate the number of atoms in the universe at something like 10 to the power 80. So this number is like 10 to the power 10,000. So this is just enormous. So yeah, this is enormous. This is huge, but this is a finite number. And the fact that this is a finite number is really important, because in mathematics, when you deal with finite quantity, and when you deal with infinite quantity, like the things, like they don't have the same behavior. But here we have a huge number, but this is not the infinity. This is a finite number. So that's why it will be really, really cool. All right, so yeah, basically you can formalize this in such a way. So by defining yeah, the matrix like this. So this is not really important to understand. What basically could be important is that, yeah, as you have seen, there are a lot of zero in this matrix, zero probability, exactly 0. This is because, yeah, so all sequences are not mapped together. And yeah, you have a huge number of 0. And okay, this number of, like the proportion of non-zero element in this matrix is something like this. So this number, you can approximate this as 1 over t to the power k minus 1. So in the case of GPT-3, it is 1 over, like, yeah, 10 to the power this number minus 1. So this is ridiculously small, but it's not 0. It is just ridiculously small. All right. So yeah. So basically, maybe you okay. The problem is that with such a huge matrix, so as I said, 10 to the power 80 is the number of atoms in the universe. Obviously, you cannot store this matrix. This is impossible because it's too huge. But what you can do, and like as it's done in this funny tweet, basically, if you have the model weight of your language model, if you have a few GPUs, like you can have access to the row you want in this matrix in just 1 second with just one pass. You just have to input the sequence you are interested in. And yeah, basically you will have this. So yeah, basically you can store the model weight in a USB key or something like this, something like you can have in your pocket, and you have a few GPUs. Basically, you will have access to the row you want in this matrix. And okay, so the matrix cannot be stored. So is it really useful? And I will answer yes, because you can now connect LLMs to the theory of finite Markov chain. And we have a lot of theoretical results that can explain to us how LLMs, like the dynamics of LLMs. And okay, maybe to start with a pretty simple language model, I will consider, yeah, a baby language model, as I enjoy to call it. So basically, what I will consider is a vocabulary space of only two values, 0 and 1. and a context window, a really small context window of 3. So basically, it will lead to a state space of size 14, so which is pretty small, and you can store this kind of matrices. And yeah, also I will. So basically, this LLM is transformer based, so it has a number of parameters. So this is a number of parameters. But yeah, basically, you can have this kind of matrices. You can store that. You can store them, and yeah, basically it tells us that you can sample like you can generate as ChatGPT does when you are prompting something to ChatGPT. You can generate the next token, the next word, by just doing a matrix multiplication and then sampling on the result, right? So this is the equivalence, but you know that in practice for big LLMs, when you cannot store the matrix, you will just do a forward pass and then sample, and that's it. But more importantly, this finite state Markov chain theory can give us some unknown insights about LLMs. So I will talk about something that we call a stationary distribution for Markov chain. So basically, this is like this represents how a Markov chain will act asymptotically. So yeah, this is the kind of distribution that remain invariant when you multiply by the matrix, and you can obtain this kind of distribution by just taking a huge power of the matrix. And the really important result of the Markov chain theory, of finite state Markov chain theory, is that when you have a finite state Markov chain, if the Markov chain is finite, you have the unicity and the existence of a stationary distribution. So it just tells us that all our large language models, they just have a stationary distribution. The stationary distribution exists, and the stationary distribution is unique, right? So this is a really good insight. And if we take our toy model again, we can just visualize the stationary distribution by just computing a huge power of the matrix. And yeah, as you can see, you have, so the matrix tends to a kind of matrix with the same rows, and this row is a stationary distribution. So thanks to the Markov chain theory, we were able to derive a convergence rate for this Markov chain, like for the LLM Markov chain, and this rate will basically, it depends on like the value of the transition of the Markov chain. And yeah, so here you can see that basically with an LLM, like for example Llama 2 or Llama 3, to reach the stationary distribution, you will have to do 10 to the power 9 token inputs, which is quite huge, but which is possible. So the Markov chain theory gives us insight about the fact that you can reach a stationary distribution. So yeah, so some critical behavior of an LLM just by inputting the LLM a huge number of times. And yeah, we have also insight that on the fact that it depends on the temperature of the LLM. So yeah, not really important, but if you have questions about this, feel free to ask. All right, so yeah, basically this was for first result that we can obtain thanks to the Markov chain theory. But also thanks to the Markov chain theory, you can obtain really nice generalization results. So often in machine learning, we have a question, and the question is that how far our model is from a ground truth, right? So basically, we can ask us the question how far our matrix our LLM is from some kind of universal distribution, universal distribution of the data, right? And another question is that, okay, basically you can train an LLM with a certain amount of data. So for example, for GPT-3, it was trained for this amount of data. But basically in the matrix, you have this number of non-zero elements. So you know that there is a huge difference between this number and this number. And yeah, one question is that, okay, how can a model generalize on unseen data? So basically you haven't trained your model on a certain amount of data, but the model is able to generate answers without training on the specific data. So yeah, in learning theory, what we do to answer this question is to establish a generalization bound to solve what we call the generalization problem. So basically you define some risk, some empirical risk, which is related to which is a kind of distance between the reference matrix and the model matrix. And you have the ideal risk. And basically you want to bound the difference between those terms, and by doing this you solve the generation problem. So what we have done in our paper is that we have done really weak assumption on for example, the pre-training data. We have said that basically the data we use to train LLMs are dependent random variable, where in a vast majority of works, people just do the hypothesis that the data are independent. And we also just have done one hypothesis on the transformer architecture. And by doing just this, we were able to derive this kind of generalization bound with this B term and a term with the complete matrix, which tells us how much the data are dependent. And yeah, basically other terms are related to the architecture. So just the sort of vocabulary size, the bound on the last layer, and etc. etc. But maybe if you want a more fine-grained bound, you can do more hypotheses on the architecture. So basically you can do assumptions on the bound of each layers, and if you do this, you can obtain the same kind of bounds, but those kind of bounds will be depth dependent and parameter dependent. So for example, you will have this kind of R, so R, which is the embedding dimension of the large language model, which is another characteristic of the model, H, which is the number of head of a transformer. And basically by doing this, you can choose the you can find the optimal choice of this kind of parameter. For example, for this ratio, you can find the optimal ratio, right? So to design the best LLM you can imagine. And yeah, so we have this kind of results. And maybe one question that arises is, okay, this kind of results are nice, but basically I want to answer the question, how much training data do I need to be epsilon close to my reference matrix? So we call this kind of formulation sample complexity. We choose the previous bound just to give you the number of training data you need to be epsilon close. So basically to have this result, so to be epsilon close in terms of distance to your distribution, you will need something like more than this number of a training example. And this number depends on the B number of the previous theorem. So for example, in this case, it depends on this. So you know perfectly how much training data you need to be epsilon close to your reference distribution. So this is quite a huge result, and thanks to this Markov chain point of view, yeah, it helps to know to answer this kind of question for such big and huge model, big LLMs. All right, but like the problem with this is that, okay, we have theoretical result, but like this is costly. Like doing training of an LLM, this is really costly. We can really like verify this. So in our work, we really tried to, yeah, to just have a numerical experiment about our results. And to do so, we instead of just focusing on pre-training, we also looked at in-context learning. So what is in-context learning? Maybe I will just introduce and maybe have experienced these things while playing with ChatGPT. Basically, in-context learning is when you prompt something to your language model, and you give like, for example, you prompt a sentence, and you tell the model that the sentence is positive. Then you do it for another sentence, you do it for another sentence, and after you just prompt a sentence, and you will ask the model to just tell if yeah, the sentence is positive, neutral, or negative, and it will automatically learn like based on the previous prompts, learn the fact that, oh, okay, this is a positive sentence. And all of this stuff are doing during inference. So this is kind of learning property during inference. So just by prompting your LLM, there is no training, no training. So this is cool because this is not as costly as model pre-training. You just have to prompt the LLM. And also, if you design well your in-context learning problem, you can have access to a ground truth. You can have access to a ground truth matrix. So you can, at the end, plot yeah, this kind of terms, because yeah, in this kind of terms, you know, you need to know the ground truth matrix, right? So yeah. And what we decided to do is to basically design our problem as a learning Markov chain problem. So imagine you have a D-state Markov chain, you will try to in-context learn this Markov chain. So yeah. So this will be what we prompt to the LLM. And yeah, so you know that Markov chain had a solid boundary, and you have some characteristics related to Markov chain, such as mixing time. So yeah, we just define this because it will appear on the bound, and also by defining yeah, such a distance between parameter sets of an LLM, you can derive this kind of results. So basically, you can bound the theoretical risk by two terms, sum of two terms. So the first term is what we call the distribution shift. So basically, the fact that if you train your model exactly on the data before, on the data you will prompt during the in-context learning before, this term will vanish. But the fact is that, yeah, the challenge is that you have not seen those data during training. So you have this term that appears, and also you have the classical term, the classical previous term. So with this constant and the number of like the length of the input, and yeah, this mixing time. And basically, what is really important in this is the fact that the B term depends as log of D, where D is the state of the Markov chain. So it means that if you have a huge state-based Markov chain, it will scale as a log of D, and you will see in the experiment why is it important. So yeah, about the experiments. So yeah, our goal was to verify if our bonds were like connected to real world LLMs, and yeah, we just took, I don't know, real world LLMs, so Llama 2, Mistral, and Gemma 2, which is more recent, and basically what we do is that we generate random Markov chains. We input this into the LLM, and we verify that it follows the bound. So this is the bound. Basically, this is the bound given by the theorem. And yeah, the more recent the model is, the more it follows the bound. So this is really cool. And also in the right figure, you have a dependence on the mixing time. So we were also able to show the dependence in just this term, like just the fact that this term appears, we show a dependence in real world LLM. So this means that our bounds are non-vacuous, and that that they really reflect, like the theory really reflect what happens in practice. So this is really important when you do experiments. And yeah, so now maybe a last experiment. What I told you before is that like in the B constant, there is a log D, where D is the number of states of a Markov chain. So basically, what we have done is that we have compared our inference, our in-context learning method of the LLM with the baseline method to learn Markov chain on the fly, which is to just count the transition. And this method, some researcher has shown that it scales as D, as a square root of D, whereas our method scales as square root of log D. So when D is small, for example, in the left figure, D is just equals to 3. So basically, it is basically the same. But when D is really huge, so in the right figure, D is 700. So when D is 700, this number like struggle to like the number and ICL. When n ICL is small, so for example 10, the fact that here there is 700 just leads to a plateau. Like you just have a plateau. Your error doesn't decrease, and the fact that our bound is in log of D just says that, okay, if you have a huge number of states of your Markov chain, it will not plateau, because log of D, when D is equal to 700, is a small number. So this means that, okay, also our bound are really each term in our theoretical result are really verified in practice. And yeah, this is why this is why basically this is important to do an experiment, that it was one of our goals in this project, to try to see that real LLMs fit our theory. So yeah, basically now it's the end of the presentation. So yeah, just a take-home message, just to recap. So in the paper we have explicitly characterized LLMs as Markov chains. And even if those are huge state space Markov chain, you can derive really cool theoretical results. So theoretical result on stationary distribution, theoretical result on generalization, and on in-context learning. And also, you can see that real-world LLM, even the most recent, just verify the theory we derived through the Markov chain mathematics. And yeah, so those are the most important contribution of the paper. But yeah, feel free to just read the paper. If you have questions, feel free to just ask. And yeah, so thank you for your attention. And yeah, thank you again.
Yep. Awesome. Thanks, Oussama. And these are very interesting observations for sure. Couple of questions actually. So do you see any influence of the model size and the context window on the behavior to Markov chains? For example, 1 billion model versus, let's say, 70 billion model, 2,000 context window versus, let's say, 1 lakh, 100,000 context window. So have you done experiments on correlation with model size versus the context window lengths?
So basically, yeah, as we just said, when you increase the context window, the state space, the size of your Markov chain will just explode.
Yeah.
But at the same time, when you have a bigger context window, you can like process longer sequences. So and that's why current LLMs have they have context windows like the number is like I don't know 100 yeah I think yeah 10,000 or stuff like that. So context window are becoming bigger and bigger because you need bigger context window to have like to have better understanding of the language. And basically this is possible only if you have enough data, enough clean data, enough if you can scale your architecture like if you can build an enough like a huge model, and if you have the computational resource. So if you have all of this, yeah, basically you can so there is an impact on the quality of the language modeling.
Okay, got it. And one more question on the behavior of the LLMs, for example. For a larger context, like we have seen different kind of behavior between, let's say, ChatGPT versus Claude, right? Claude captures a lot of, or at least preserves a lot of information at the later part of the context. If I'm not wrong, something of that sort, where, let's say I've given 100 facts across the context, it remembers the facts which are at the last sentence, for example, or at the last context values. Whereas ChatGPT has a different kind of behavior where, so it remembers more in the first stage of
Yeah,
context.
yeah,
Is there yeah, is there some
yeah.
intuition that we can draw from this kind of behavior? Like, is this a behavior that we can maybe replicate or understand how the models are behaving?
So basically, I think that this kind of behavior are really specific to the way you train your model. So you know that ChatGPT and Claude are closed source models, so we don't really know what they do when they train their models.
Mhm.
Perhaps, so yeah, basically, okay, I will just share my screen again, sorry, just to show, yeah, perhaps, yeah, in this figure, I have heard a video of Andrea Scarpacci that said that, okay, like when he was at OpenAI, he said that, okay, often we train language models with really short sentences that that don't fit the whole context window, while other strategies of training are to just put full sentence, like just fit the context window fully. And maybe this is because of those different strategies of training. Like the fact that, yeah, as you said, for example, Claude is better when on the last part of the sentence, because, for example, ChatGPT was more trained on short sentence, and after they grew up the length of the sentences. So yeah, I think this is related to like training secrets, and to be honest, I don't know the training secrets
Yeah.
of Anthropic and of OpenAI. So yeah.
Sure. No, that's okay. Actually, this actually brings me one more question on in-context learning, right? Like
Yeah.
if you look at GPT-4o, for example, the
Yeah.
reasoning model,
Yeah.
it's actually creating a dynamic chain of thought, prompt or a chain of thought process.
Yeah. Yeah.
Uh, so, can we use this behavior to maybe create a right training cycle for reasoning kind of models? because these models are necessarily a Q-learning kind of model, which has these chain of thoughts as the inputs, right? Yeah. So do you see some applicability on behavior of Markov chains versus the chain of thought model training?
Yeah. So basically, when you do chain of thought, basically what you do is that you navigate through the transition matrix to basically to reach part of the transition matrix that are like not accessible directly if you just treat the sequence without channel of pointing. So yeah, I thought about a bit about chain of thought, about how we can apply chain of thought to this, and yeah, my first idea was to see, okay, basically they navigate through the matrix to reach some part of the matrix which is not directly accessible, and which a lot of information, because basically when you navigate through this matrix, it's like you fill in the context. And yeah, with channel of thought, they spend more time at inference. So by spending more time at inference, they just they are going deeper in the matrix, so that they have better a better quality of answers. So
Yeah, got it.
I think we can definitely connect a chain of thought to this kind of behavior.
Okay. And is that also a way to validate the model performance, or let's say model stability, for example? Is there a baseline that could be derived from Markov chains, let's say on a specific data, and compare different model behaviors and say, this model behavior is probably more stable, more reliable, whereas the other one may not be because it's underperforming from the baseline? So is there a way to use this as a benchmarking or a model performance criteria?
Yeah, understand the question. I think this is one limitation of this work, because to do such benchmark, you have to have access to the huge to the full matrix, which is not possible, because you basically you cannot store the full matrix. You can just have access to small part of the matrix. But yeah, I think to do benchmark of stuff like that, you really need to have access to a whole matrix, and this is certainly not possible. So yeah, this is a limitation of this work, clearly.
Okay. Got it. Awesome. Yeah, so that's all from my side. Let's see if anyone has any questions. Yeah, so there is one question from Joshi. You discussed the influence of temperature on convergence. Could you elaborate on how temperature affects model performance and inference, whether it can be used as a tool to manage trade-offs between creativity and stability in LLM outputs?
Yeah, so basically, just to recap, the temperature is some hyperparameter that you fix. So this is a number between 0 and infinity. So basically, when this number is 0, you have like the model tends to produce more deterministic output, as it will just pick the R max of the probability distribution. It will just pick the most probable next token. And when you increase the temperature, on the other hand, it will have the effect to like flatten the distribution. So you will produce more, more creative answers. And yeah, basically you have to set this parameter to have a trade-off. So the default value is 1 basically, and if you, for example, if you open chatgpt.com, you can change its value, but its its value is locked. Like you can go greater than 2 or something like this, or 3. I think it's 2. So yeah, basically this is because they want to keep this good trade-off area for the temperature. So yeah, I think because you you want creative answer, but you also want stable answer. So yeah, don't play too much with this parameter.
Got it. I think that makes sense. Yeah, let's see if there is any questions. I think that's all. Yeah, awesome. But otherwise, what is your next excitement? I mean, where do you see this going towards to? And what is your next area of research or problem statements that you're currently working on?
Yeah, so currently I'm interested in like, okay, I worked on this first side of generative AI, which
Mm-hmm.
are large language models, and now I'm more interested in, like, you know, all of these diffusion models, because okay, maybe you have guessed that I have a pretty mathematical background. So in diffusion model, there are a lot of elegant mathematical things. So yeah, actually, I'm interested in diffusion models, and yeah, like
Got
they're
it. Awesome.
like same, you know, deriving mathematical insights that explain the behavior of diffusion model, for example, in order to generate images or stuff like that.
Got it. And again, a very controversial question. So, do you see these LLMs go to a stage where they can start solving these problems? There is a bunch of claims that the current GPT-4o is a PhD level kind of model. Do you
Yeah,
agree, disagree, or where do you see that going to?
yeah. To be honest, I experienced the fact that, like, I personally experienced the fact that, like, prompting a hard problem to O1 preview,
Yeah,
and I was really impressed. Like, I was like, okay, it's strong. And I think, I don't know if there will be a limit, because, you know, nowadays we are, you know, there's Ilias Escobar that said that we reach like a plateau
yeah,
now. And I don't know if we can go like beyond this, but like the current state of the art, like this is really good. And okay, if we can go beyond, definitely it will be really, really, really good. But it's already really, really stunning, really good. So I,
got it.
yeah,
Yeah, I think all
I'm
of us are
more,
very excited.
yeah, yeah. Basically, I'm more enthusiastic. Yeah,
Makes sense. Great, awesome. Thanks, Oussama, for taking time. So we will share the recording, and thanks for giving us time once again.
yeah. Thank you, thanks a lot. And yeah. So you will share the contact by mail or something like that?
Yes, I'll share
Okay,
the
perfect.
recording. So
Okay, nice,
yeah,
perfect.
sure.
Excellent, excellent. Okay,
Awesome. Thanks, everyone.
thank
Let's wait
you.
for the next session. So thanks, Oussama. See you.
Thanks. See you.